All right, so welcome back to the next lesson for Calculus 2 prep material. So this lesson, we're actually going to be going ahead and talking about the complex numbers, which is an important concept that will be taught later on. So I think it's best to go over like the primary concepts of the complex numbers, and then we could actually go on with the uh, rest of the Calculus 2 lessons. Okay, so let's have a look at the complex number first. So a complex number can be represented by an expression of the form a plus bi. So that's the definition of a complex number, where we have a and b to be the real numbers, and we also have the value I that is actually denoted by the square root of -1. So the complex number can actually be represented by an ordered pair, a and b. So if we have the a and b here, this is also the same as the a and b as an ordered pair, and which this could actually be plotted in the plane, which is sometimes called the arcing plane. So, for example, the complex number I is also the same as saying the 0 plus 1 plus I. So this line is by saying, well, if a is equal to 0 and b is equal to 1, then we could just have the complex number. And it's also corresponding to the point 0, 1 on the arcing plane. So let's have a look at the following complex numbers and see how we could actually plot this on the grid here. So we have, for the first one, we have 2 plus 3i. So on the complex plane, so this is going to be where we're going to let the a here, so this part is going to be the a part. This is going to be the b part here. So here we have that a is going to be 2. So if we go to the grid here, we see that, well, a is going to be here. So this is 2. And we're going to go 3 up. So the b is going to go 3 units up because this is also corresponding to the point 2, comma 3. So that means 3 is going to be here. So this is going to be the complex number. So I'll call this a. Same thing, similarly for the complex number for b, this is actually going to be corresponding to the point 3, -2. So we're going to go to 3 here, and we're going to go -2. So that's corresponding to this complex number, which I'll call it b. Same thing for c as well. We have -2 minus 2i. So this is also the same as the ordered pair from -2 and -2. So that means if we have -2 on this side, so that means this coordinate here is going to be our c. And last one, well, d here, we have -4 plus 2i, which is also the same as the ordered pair -4, 2. So that is, so -4 is over here, and 2 is up here. So this is 2. So that's point D. So that's the plot on the complex plane or the arcing plane. So let's have a look. The real part of the complex number a plus bi is the number a. So we call the number that is without the I the real part of the complex number. Sometimes it's also denoted by R, this type of R, or sometimes you would also see it is also denoted by RE of a plus bi, which is also similar. Sometimes people would like to change it up a little. It's fine. So that means on the plane here, instead of this a, we would actually say this is actually the RE of, let's say, a complex number z. And we also have the imaginary part of the real number of the complex number, which is the b value. So this is going to be the b value, which is also denoted by this notation here. Sometimes you would see it also be denoted by im of I a plus bi, which is equal to b. So in other words, we could also change this b here so that it becomes the imaginary part of Z. So sometimes we like to denote the complex numbers using Z, W, and so on. So for example, let's say we have the complex number 4 minus 3i, then the real part would just be the 4, which is just the number without the I in front of it. And the imaginary part is going to be the -3, which is the one that is actually attached to with the I. So once, as I mentioned, we will be using Z to denote a complex number, or it could also be W as well. So let's have a look at some operations with complex numbers. So the sum and difference of two complex numbers are defined by adding their real parts together and their imaginary parts together. So if we let Z be A plus BI and W be C plus DI, so then we would actually have Z plus or minus W. So we're going to first of all substitute A plus BI and plus or minus C plus DI. Now, rearranging some of the terms a little, I'm going to go ahead and do a little bit of switches. So we're actually going to say A plus or minus C plus BI plus DI. Or actually, this should be plus or minus, yep. So we could also say A plus C plus minus I B plus or minus D. So we see that the real part of Z plus W or minus W is going to be A plus or minus C, while the imaginary part is actually just going to be the B plus or minus D. So the product of the complex numbers is defined so that the usual commutative and distributive laws also hold. So say we want to multiply the complex numbers. So say we have Z multiplied by W. So we have A plus BI multiplied by C plus DI. So we're going to use the distributed property. So we're going to use the FOIL method. So we're going to distribute this first. So we have AC plus ADI minus or plus ECI and then plus BDI squared. Now here's one thing to note. If we have that I is the square root of -1, then that means I squared has to be equal to -1 as well. So that means this I squared here is going to change to a negative. So that means what we would have is that AC, and I'm going to group them together. So that's just going to be BD. So that's in 1. And then we add AD plus BC. I's in each of these. Or we could also say AC minus BD plus I AD plus BC. So we see here that the real part of Z plus W is going to be AC minus BD, where the imaginary part of Z times W is going to be the AD times BC. So let's go ahead and have a look at an example where we're going to multiply these two complex numbers together. So we're going to use the formula that we have just found out. So let's multiply these. So 1 minus, so -1 plus 3i multiplied by 2 subtract 5i. So if we let A be -1, B be 3, C be 2, and D be -5, then we could just go ahead and put it into this formula here. And so our A is going to be -1, our C is going to be 2, plus B is going to be 3, and D is going to be -5. So that's for the first complex now, for the real part. And for the imaginary part, we still have the I on the outside. So our A, once again, is -1 multiplied by -5 plus, oh, sorry, this should be a negative. So plus here, our B is going to be 3, and our C is going to be 2. So what that means, we have negative 2 plus 15. So that is negative 2 plus 15, and plus I, which is times 5 plus 6, which is equal to 13 plus 11i, which is the complex number after you multiply these together. So it's always convenient to have the complex numbers in the form of a plus bi. It just makes things a lot easier. So division of the complex numbers is very similar to like rationalizing a radical expression. So let's say for a complex number, a plus bi, then we define the complex conjugate here. So the complex conjugate is the opposite or the conjugate of the complex number, where we denote it by z bar, which is equal to a minus bi. So as a visual, say you have a complex number that is going from that has the order pair a to b here. Its conjugate is actually going to be going in the opposite direction, which is going to be a comma minus b. So this part here is going to be your z bar. This is going to be your z here. So that's the complex conjugate. So it's going to be the mirror over the x-axis, which is the complex conjugate. So to find the quotient of two complex numbers, we multiply the numerator and the denominator by the conjugate of the denominator. So if we want to express this complex number in the form of a plus bi, as we said here, we have to multiply the numerator and the denominator by the conjugate of the denominator. So the conjugate of the denominator here, so let's say z bar, or say z was 2 plus 5i, then the complex conjugate, z bar, is just going to be 2 minus 5i. So we're going to multiply both the numerator and the denominator by that value. So what we have is negative 1 plus 3i divided by 2 plus 5. So if we multiply here, so multiply by 2 minus 5i minus divided by 2 minus 5i. So what we get in the denominator is actually a difference of squares here. So in the denominator, we just get 2 squared minus 5i squared. And in the numerator, we just get negative 1 plus 3i and 2 minus 5i. Well, we actually found what the complex number of the numerator is from the previous example. So we could just go ahead and put that. So we have 13 plus 11i divided by, so the denominator here, what we get is 4 minus 25i squared. But I squared is negative 1, so that's going to become 4 plus 25. So that means we're going to get 29 as a result. So now we want it in the form of a plus bi. We're almost finished. So all we just had to do is separate the 29 for each term so that we would just get 13 over 29 plus I, or if you want, you could put it 11 divided by 29 multiplied by I. So this part over here, the 13 over 29 is going to be our A. The 11 over 29 is going to be our B. So that is the division of the complex numbers. So these are some properties of the complex conjugate where we have, if we have the conjugate of z plus w or minus w, that would just be the sum of the conjugate of z, the conjugate of w. If we have the product of the conjugate z times w, that would just be the conjugate of each individual ones. And if we have the conjugate of z to the power n, it would just be the conjugate of z to the power of n by itself. Now here, we now want to be talking about the modulus or the absolute value, or sometimes called the norm of the complex number z. So the modulus, I'll usually call it the modulus, is the distance from the origin to the ordered pair A to B. So we're actually going to be going from 0 to 0 to the point A to B. So visually, say we have our origin here. Remember that the complex number is always going to be represented as an ordered pair. So A plus BI is also the same as the ordered pair A to B on the plane. So A to B, say we take a point here, that is going to be our A to B. So that means if we draw a line here, what this line represents is actually our distance or the norm or the modulus of z. So this is the modulus of z. Now the formula for the distance, we should be kind of familiar with it. So here we have by Pythagorean theorem, the norm of z here. So norm of z is simply just by Pythagorean theorem. So if this length here is going to be your b, this length is your a, then that means the norm of z is simply just going to be the square root of a squared plus b squared. Okay, so that's the modulus here of a complex number. So let's have a look at the next example where we have if z is equal to a plus bi, we want to find z times z bar. So here noting that the z bar, which is the complex conjugate, is going to be a minus bi. So we're actually, if we put this together, so we have a plus bi multiplied by a minus bi then. Now we also have a difference of squares here. So we would just have the a squared minus bi squared, which is also the same as saying a squared minus b squared times I squared. But since I squared is -1, this is also the same as a squared plus b squared. But what is a squared plus b squared here? Well, we already just found it above, a squared plus b squared. If we just take the square root or square of it, we would just get, so the norm of z, or the modulus of z, is also the same as a squared plus b squared. So that means the one that we just found, a squared plus b squared, is also the same as the modulus of z squared. And that's the fun thing about complex numbers. You could explore a lot of the different concepts that would be really interesting to see as a result. All right. So the next section here will be having a look at how to solve complex equations. So we're familiar with solving polynomial equations, but in this case, we want to be able to solve polynomial equations that can involve some complex numbers. So we could think of I as a square of -1. So we would also have negative I squared, which is I squared -1, and so on. We say that I is the principal square root of -1, and we would also write that I is equal to square root of -1. So in general, if C is a positive number, then we would say that, well, we would see I to the power of C. We could also write this as I to the power of C. But that also depends on what the value of C is. But sometimes if you have maybe, say, if we try to evaluate I to the power of 1, that is going to be I. But I squared, we have -1. I cubed is also the same as I squared times I, which is negative I. Or we have I to the power of 4, which is I squared times I squared, which is equal to 1. And then the cycle just keeps on repeating. So if C is actually, I need to make sure this is a integer, positive integer. So then we could actually have 4 different options here. So, but this is, note that I to the power 4 is also the same as I to the power of 0. So that means every multiple of 4, so 0, 4, 8, 12, 16, and so on, is actually going to be the same value, I, or 1. So that means if C is equal to a multiple of 4, we could also see that, well, if we have I to the power of 5, we could write this as I to the power of 4 multiplied by I. So that means we could have a multiple of 4 plus an additional I. So that would always give us an I here. If C is 4k plus 1, I'm also going to continue this over here. So we could also see that if we have I squared negative 1, every multiple of 4, so 2, 6, 10, so on, is always going to be negative 1. So it's a multiple of 4 with an additional factor of 2, or additional addition of 2. So we would have negative 1 if C is equal to 4k plus 2. And last one, you could also see that if we have 3, so 3, 7, 11, this would be negative I if C is 4k plus 3. So that would be a multiple. So C could either be any of these 4 numbers here, depending on what the value of k is. Okay, so with the convention above, the usual derivation and formula for the roots of the quadratic equation are even valid when b squared minus 4ac is less than 0. So remember that the quadratic formula, if you have x, we have minus b plus or minus b squared minus 4ac divided by 2a. Then the inside part, if this is less than 0, we know that it does not work in the real case, but we can actually go ahead and work with the complex case using complex numbers, using the I that we have worked with to actually solve all the solutions. So if this is less than 0, we could find more solutions. For example, let's say we solve x squared plus x is equal to 1. So if I use the quadratic formula here, we have x, which is equal to minus 1. So here, a is equal to 1, b is equal to 1, c is equal to 1 as well. So that means if I have 1, negative 1, plus or minus b squared, which is 1's, minus 4 times 1 times 1, all of this is divided by 2. And what that means, so we have negative 1 root negative 3 divided by 2. But negative root of negative 3 is also the same as saying negative 1 plus or minus I root 3. And then divided by 2. So that means the solutions are going to be negative 1/2 plus or minus root 3 over 2I. So we have complex numbers now that will, if we allow complex numbers as solutions, then every quadratic equation will have 2 solutions. More generally, it's also true for any polynomial equation. So say we have a polynomial of the form a n, zn, a n minus 1 z to the power n minus n, and so on, and we set all of that equal to 0, where the degree here is at least 1, then every polynomial equation has a solution among the complex numbers. So that is known as the fundamental theorem of algebra, which is an interesting result for complex numbers. So next section, we'll actually be having a look at the polar form of complex numbers. So remember that cosine and sine are represented by a unit circle. So remember that we have cos theta is given by x over r, and sine theta is equal to y over r. So if we put this z is equal to x plus yi, so that means if we put x and y instead into the x here and the y into yi here, we could actually write this in terms of polar coordinates instead. And we'll talk more about the polar coordinate stuff later on in the prep book. So for example, if we substitute it in, so if we substitute the r, we could see that we have z is equal to r cos theta plus I sine theta, or r times I sine theta. Or in other words, this is also the same as saying r cos theta plus I sine theta, where r here is actually going to be the length of the complex number, and I is the complex number root -1. So say we go from the origin to a point A to be x. This is going to be your xy here instead now. Now, to find a complex number, to change it to this form, what we actually need is a couple of things. So the first thing is that we need the modulus of z, or which is also going to be your r here. The other thing that we would also need to know is what is the angle between the horizontal and the arm, or the modulus of z. So this is the angle that we need to know, which is going to be given by theta. So that's how we could actually use the polar coordinates to actually change this. And so we usually have z is equal to x plus yi. So we're changing it to the polar form, which is given by r times cos theta plus I sine theta. So the angle theta here is usually called the argument of z, and we write theta is equal to the arg z. Now, note that arg z is not unique, meaning that you could also have two different arguments of z, or like any two arguments of z differ by an integer multiple of 2 pi, right? So let's have a look at some examples. So let's say we have the complex numbers given by z, which is 1 plus I, and w is root 3 minus I. So remember, we need two things. We need the length of r, and we also need the angle form. Now, the angle form is usually determined by the tan inverse of the x and y. So if we want to know what theta is, so if this is y, this is x, we could go ahead and use tan inverse of y over x, which is the opposite over adjacent here. All right, so that's one thing we could also. And also note that, well, r is also the same as the modulus of z, which we found to be the square root of x squared plus y squared. So those are the two useful formulas that we will actually be using for the next little while. So let's go ahead. So for the first part, 1 plus I, so we know that x is going to be 1, y is going to be 1 as well. So that means the modulus, or r, is just going to be 1 squared plus 1 squared, which is also going to be just square root of 2. And then we would also have to find our theta, which is equal to the tan inverse of, so y is going to be 1 x is going to be 1, so that's tan inverse of 1, which is also the same as pi over 4. Then we would also just go ahead and put this into the polar form, which is z, which is root 2, multiplied cosine of pi over 4, plus I sine pi over 4. Now, if we try to evaluate this by hand, so this is going to be root 2, or 1 divided by root 2 here. This is going to be 1 divided by root 2 as well. We would see that, well, if we distribute, evaluate everything else, we would get this exact form back here. But that's not the point of the polar form. We want to leave it as is. Now, let's do the same thing for W now. So once again, we need to know the modulus. So R here, which is the modulus of Z, is the square root of root 3 squared plus -1 squared. So that means the length here is going to be 2. And also now, theta is also the same as saying, well, tan inverse of y, which is -1 divided by root 3. Now we have to pay attention to what quadrant this actually lies on. So because the y is going to be negative and the x is going to be positive, so that means it's going to lie somewhere in quadrant 4. This point here, maybe. So that means if we try to evaluate tan inverse of -1 over root 3, we should be able to get 11 pi divided by 6 here. And that is going to be the argument. So that means if we substitute everything back in, we would just obtain that W is going to be 2 cos of 11 pi over 6 plus I sine 11 pi over 6. And if we evaluate everything else, we would obtain the original complex number. So the polar form and the complex numbers gives insight into multiplication and division. So these could actually be helpful if you want to know some of the trigonometric identities, in particular being the compound angles, double angles, triple angles, and so on. So let's go ahead and try to find the product between the two. So if Z is equal to R1 times cos theta plus I sine theta, and W is R2 times cos phi plus I sine phi, then Z plus W here, we would just have, by multiplying the two norms or two moduli, and we would also have the cos theta 1 or cos theta I sine theta, and multiply by cos of phi plus I sine of phi. And so we just want to be working on the distribution of this. So multiplying cos theta, cos of phi, and we have plus I sine phi, or I sine phi, cos theta, plus I sine theta, plus cos times cos phi, and we have I squared sine theta sine phi, like that. Okay, so now we would just have to work on the inside a little. R2. So we could separate them into their real and imaginary parts now. So noting that this one and this one is going to be the real part. So I squared being the -1. We have R1 times R2 times. So for the real part, we're going to have cos theta cos phi minus sine theta sine phi. And also, we have plus here, I, so we're actually going to be common factoring out the next term. So we have this one and this one. So so we have sine theta cos phi plus sine phi cos theta. So that's what we have found here. Well, we could also simplify things a little bit further because I know that this part is also the same as cos theta plus phi. And this part over here is actually just going to be sine theta plus phi here. So that means the multiplication of two complex numbers in their polar forms are actually just going to be R1, R2, cos theta plus phi plus I, so I sine theta plus phi. And that is the product of two complex numbers in their polar forms. All right, so now let's try for Z and W now. Let's see what we can get. Okay, so for Z divided by W, what we actually obtain here. So I'm going to do something similar. So I'm going to zoom in. So R1 divided by R2, I'm just going to keep the divisions out. So we have R1, R2. And so Z here we know is going to be cos theta. So we have cos theta plus I sine theta. And we're dividing this by cos theta or cos of phi plus I sine phi. So now I'm also going to be multiplying by the complex conjugate, cos phi minus I sine phi. Cos phi minus I sine phi. All this divided by cos phi minus I sine phi. And so what we get in the denominator, which is just a perfect square or a difference of squares, so that's going to be cos squared plus sine squared, so that's going to be 1. So so this denominator part is all going to equal to 1. Okay, so that means we don't really have to worry about. So this part and this part is equal to 1. So we just have to work with the numerator. So that means R1 divided by R2, well, we just have cos theta plus I sine theta times cos phi minus I sine phi. Well, that is also the same as saying R1, R2, multiply, so distribute now, cos theta, cos phi. Then we have minus I sine phi, cos theta, plus I sine theta, cos phi. And we also have minus I squared sine theta sine phi. Yep. Okay, so once we have this, we could separate them into their real and imaginary parts once again. So say we take the cos theta cos phi here, and this part is going to be positive sine theta sine phi. So I'm going to write this R1 divided by R2. And we would just have, so for the first one, we have cos theta, cos phi, plus sine theta sine phi. And then for the other term, we have I still, but we're going to have sine theta cos phi minus sine phi cos theta. Now, note that we could also use the compound angle identities. So the first term here is going to be cos theta minus phi. And then the second one is going to be sine theta minus phi. So what that means is that R1 divided by R2, and then we would just have cos theta minus phi plus I sine theta minus phi as well. So that is the division of two complex numbers in their polar forms. So that's the derivation for this one. And as for the last one, we're going to be deriving for 1 over z as well. So 1 over z, we know that z is equal to R1 times cos theta plus I sine theta. So let's go ahead and put that in. I'll use a different color. So 1 over z, so we know that's going to be 1 over r, and then we also have 1 divided by cos theta plus I sine theta. So once again, I'm going to multiply it by the conjugate, that being cos theta minus I sine theta, cos theta minus I sine theta. So once again, in the denominator, we're going to get, so we still have the 1 over r, multiply by the cos theta minus I sine theta. All this is divided by 1 because the entire denominator part is just going to end up being 1. So that means what we just end up having is 1 divided by r1 multiplied by cos theta minus I sine theta. Yep. And so that's true. Yep. And that's all for the third part as well. Okay. So one thing before I actually move on is that, well, let's say we have an arbitrary complex number z. So say we have z is equal to a plus bi. If we want to find 1 over z, then we could actually, so go ahead and 1 divided by a plus bi multiplied by a minus bi, so by their complex conjugate. So we get a minus bi divided by a squared plus b squared in the bottom. So that is also just equal to the complex conjugate of z divided by z times, or the modulus of z squared. So that means we could also rewrite 1 over z as this number here. So the complex conjugate of z, so if we look at the previous example, so what this z bar is actually going to be the cos theta minus I sine theta. And the modulus of z is just going to be the cos theta, cos squared theta plus sine squared theta, which is equal to 1. And so that means we would just get this as a result. Okay, so with that, let's have a look at the next part, which we'll talk about the de Moivre's theorem, which is an important concept in complex numbers. Okay, so de Moivre's theorem says that if we have z, which is equal to r times cos theta plus I sine theta, and we let n be any natural number, then we say that z to the power n, that is equal to r times cos theta plus I sine theta, all to the power of n, is also the same as saying r to the power n multiplied by cos of n theta plus I sine theta, n theta. So from the previous examples that we had a look at, if we say that, well, w was equal to z, then we would just get the complex, so that means we would have r squared here. So if w was equal to z, then phi would also equal to theta. So this part would just be equal to 2 theta, and this would be 2 theta as well. And that would also be true. So yeah. All right. So let's have a look at an example. So we want to use de Moivre's theorem to evaluate 1/2 plus I over 2 to the power of 10. So 10 is actually gonna take a long time to actually evaluate by hand. So the shortcut way to actually evaluate this is by using de Moivre's theorem. Okay, so the first thing is we need to find what r is, and we need to know what theta is. So r here, we could find by finding the modulus, which is 1/2 squared plus 1/2 squared. So that means we have a quarter plus a quarter, which is a half. So that's 1 divided by root 2. Or no, yeah. And then we're gonna find the theta. So we could just do tan inverse of 1/2 divided by 1/2, which is equal to 1. So that's just going to be equal to pi over 4. And since n here is going to be equal to 10, well, we could just go ahead and put all of the stuff in. So that means here, half plus I over 2 to the power of 10. So that means z here, well, if you write this as 1 divided by root 2 times cos of pi over 4 plus I sine pi over 4. So that means if we raise it to the power of 10 now, that means this is going to be raised to the power of 10, multiply this by 10, multiply this by 10. So that means we would just get 1 to the power of 2, 10 over 2. So that's going to be to the power of 5 now. Oh, to the power of 5. Multiplied by the cosine of 10 times pi over 4 plus I sine 10 times pi over 4. And that's how you would use de Moivre's theorem to evaluate complex numbers that are of higher powers. Similarly, if you were to evaluate this, maybe say 100, for example. So you would just, instead of 10, you would just put 100 and same process there. Okay, so let's have a look at the next theorem that talks about the roots of a complex number. So the theorem here says if z is equal to r times cos theta plus I sine theta, and let n be any natural number, then z has n distinct roots given by omega of k, which is equal to 1 over k multiplied by cosine of theta plus 2k pi divided by n plus I sine of theta plus 2k pi divided by n. And k here can only be ranged from 0 all the way to n minus 1. So the following example asks us to find the sixth roots of z to the power of -8 and graph these in the complex plane. So that means what we want to find is the roots of 8. So complex number is going to be 8. Well, 8 here, let's find the modulus first, which is equal to, so that's going to be -8 squared plus 0 squared. That is just going to give me 8. And that means theta, well, I can't use tan inverse now, but I can use one of the other trig ratios that could help. So I could actually go ahead and use cos inverse of, so that's going to be 8. So the x here is going to be -8. So that's going to give me -1, or that's also the same as pi. So that means I'm going to start from -8 here. Okay, so let's say that's going to be my 8 here. And I want to find the 6 different roots of unity. So that means I want to find for k is equal to 0, 1, 2, 3, 4, and 5. So those are the roots that I want to find. So that means my W0, which is going to be my first root, is just going to be, so this one here is just going to be 1. Assume that this is going to be just the regular modulus. So this is only for, yeah. So 0, 1, 2, 3, 4, 5. So that means k here has to be 0. So we just have theta divided by n. So that'd be equal to r. So that'd be 8 times cosine of theta, which is pi, divided by 8, plus I sine pi over 8. And so that means it's going to lie somewhere in the first quadrant. So let's say it lies over here. Maybe there. Yeah. And then W1, so W2, omega 3, omega 4, and omega 5. So that would just be 8. So the modulus, which is 8, to the power 1 divided by 1, which is 1. Oh, sorry. The omega of 0 should just be negative 8 here, which is the 0th root. So it should be maybe there. So for the first one, then, we would just have 8 multiplied by cos. So we have theta, which is pi, plus 1, so 2 pi, divided by 6. Yeah, because 6 here, because we have the n to be 6, which is the 6 roots. And then we add I sine pi plus 2 pi divided by 6. So that's also the same as saying, well, so we would have 8 cosine pi over 2 plus I sine pi over 2. So that means we're just going to have 8 times 1, or I. So that's going to be 8i. So that's going to lie somewhere over here. And we would do the same thing. So we would also have 8 to the power 1/2 now. So that's root of 8. Cos of pi plus 4 pi now, divided by 6, plus cosine I sine. So we have I sine of pi plus 4 pi divided by 6. And so this one should just be 8 to the power 1/2 to the power, so that's going to be 5 pi over 6. 5 pi over 6. So that's negative, plus I sine 5 pi over 6. So that would be approximately somewhere maybe over here. And the process would just keep on going. So although this is not really going to be to scale. So let's try that. So we have the 0, 1, and 2. Pi over 6. Okay, so this, let's keep on going. Yep, and so W3, we get 8. So do the same thing. 8 to the power 1 over 3. We would get cosine. So we would add 6 pi. So that's 7 pi over 6. I sine 7 pi over 6. So that would lie somewhere maybe in quadrant 3. So that's maybe down here. or no, maybe down here. And then W4 or omega 4, you get 8 to the power 1 over 4 cosine 9 pi 3 pi over 2 plus I sine 3 pi over 2. So that would be down here now. And we also have the other numbers. Let me see what we get. So W5, oops, 8 to the power 1 over 5 cosine of 9 pi. So that's 10. So that's 11 pi over 6 plus I sine 11 pi over 6. So that is somewhere in quadrant uh, quadrant 4 now. So that is going to be approximately over here. So although this drawing might not exactly look as exact as I want it to be, what you should observe is that, well, this should, if you try to connect the lines of this shape, you should be able to get some sort of hexagon here. Although does not look like a good hexagon, so let me try to reconstruct this a little. Okay, so there was actually a typo on my document actually, so I'm actually gonna have to redo this example. So what we actually want instead is, so this is not supposed to be K, it's actually supposed to be N here. That is the thing that we want. Okay, so now it would be a bit easier to find the roots of unity now. So now let's say, so we, once again, we found out that the modulus here was going to be 8, and the theta here is going to be pi. So that means, well, the roots of unity is given in the general form of wk, which is 8 to the power 1 over k, or 1 over 6, since n is the 6 roots of unity. And we multiply by cos of pi plus 2k pi divided by 6 plus I sine pi plus 2k pi divided by 6. So that's what it should have actually been. So that was my mistake there. So that means it's for only when k is equal to 0, 1, 2, 3, 4, and 5. So that does not change. So that means for omega 1 or omega 0, we would actually just have, so 8 to the power 1 over 6. So cosine of pi over 6 plus I sine pi over 6. So on the graph, that would actually look be on maybe close to around here. Or if this is, so maybe around here. So that's omega 0, I'll label that. Then W1 would be 8 to the power 1 over 6. So cosine here would be pi over 2. And so the other one would also be pi over 2. And so if we calculate this, this would actually give you root 8, 8 to the power 1 over 6. So that'd be approximately over here. W2 or omega 2 would be 8 to the power 1 over 6 cosine of 5 pi over 6 I sine pi over 6. And so that would be approximately over here. Oh, maybe a little bit down further. Yep. Omega 3, you would also find something. So 8 to the power 1 over 6 cosine of 7 pi over 6. Seven pi over 6 here. So that would be down here. And omega 4, you would have 8 to the power 1 over 6 multiplied by cosine of 9 of 3 pi over 2 plus I sine 9 pi over 3 pi over 2. So that would be on the axis, y-axis. So down here. And omega 5 would be 8 to the power 1 over 6 and cos of 11 pi over 2 6 plus I sine 11 pi over 6. Okay, so those are the 6 numbers. So now here, this should be a little bit easier to look at. We see that we get a hexagon shape. So we see if we connect the lines here. So connect this. We should be able to get a polygon here. So this is actually true in general. Whenever you want to find an nth root, nth roots of unity, you would actually eventually get a circle, assuming that you let the number of sides, so in this case 6, or go to infinity. So you would eventually end up obtaining a circle that goes around all the points here, that contains all the complex numbers. Let me try to draw a better circle here. This does not look good. Yeah, so that looks a bit better. No, it does not. Not really. Okay, let me draw a better circle. Okay, and maybe so about there and about here. Well, eventually you would see that you would get a circle that's forming around the points that we have drawn, but that's the general idea. Okay, so the last bit here we'll be having a look at Euler's formula. So Euler's formula is basically saying that if you have a complex number z, and if you raise it to e to the power iz, then that's also the same as saying cosine of z plus I sine of z. For example, let's say we want to evaluate the following Euler's numbers using Euler's formula. So what we get here, if we just evaluate at pi, so for the first one, we have e to the power I pi. So everything we put in pi. So we have cos of pi, I sine pi, which is just going to be -1. So that means e to the power I pi is -1. And similarly, well, e to the power -1 plus I pi over 2, we could rewrite this a little. So note that this is e -1, e I pi over 2. So all that we have to do is change the second part, e -1 cos pi over 2 plus I sine pi over 2, which is just going to be I. So we actually have I e -1 or I over e. So therefore, this complex number is actually just I over e. Okay, so the last part here for this section is that we can use Euler's formula to prove de Moivre's formula. Okay, so let's go and see what happens if, so say we have a complex number z, n. So z to the power n, or z first of all, is equal to r n cos theta plus I sine theta. n theta. So that's what we actually want to be proving in this case. So z to the power n is given by this. If we have, well, e to the power I z, or I theta, let's say, well, this is also the same as saying, well, cosine of theta plus I sine theta. Here we'll assume that the modulus here is going to equal to 1 because of Euler's formula. So that means if I raise both sides to the power of n, so I n theta, or I theta, to the power n, cos n theta, or cos theta plus I sine theta to the power n, then that means here, well, e to the power I n theta is also the same as saying cos theta plus I sine theta to the power n. Well, if we join these two formulas together, n theta there, so now our argument inside, instead of theta, we're actually going to be using n theta. So now if we do the substitution again, we could easily see that this is just equal to cos n theta plus I sine n theta, which is exactly what de Moivre's formula tells you, is that if you have cos theta plus I sine theta, oh, let me move this down actually, raised to the power n, you would obtain this formula here. Okay, so that is actually going to wrap things up for today's lesson. So the next lesson will actually be starting with the integration section, or first of all, talking about the areas of integrals. So hopefully you learned something in this lesson today, and I will see you guys in the next session. If you have any questions, just feel free to let me know.